Hey, let's jump in to one of the most complicated topics in sequences. It's quite difficult to understand this topic through a book, and even in a classroom, without using animation, it's quite difficult to illustrate the idea behind the limit. But in this lesson, we'll talk about what is most interesting in sequences. In a previous lesson, we talked about properties of sequences, about monotonicity, decreasing and increasing sequences, and also boundness of a sequence. Both are interesting and important, but what's most interesting is the limit. And I want us to understand it in a very profound way. So to do so, let's bring back a sequence we already saw before, 1 over n, and ask ourselves, what is its limit? Formally, we write lim as the limit, n goes to infinity of an. In our case, the limit of n goes to infinity of 1 over n. What we're asking ourselves is, if we zoom out and we go far as we can, what would be the values of that sequence of an? Do they approach any specific value? Obviously, we can't go all the way to infinity, but that's the idea. Is there a trend we can see? Now, in this case, I think we can agree that the general element goes to 0. And that is actually the limit of this sequence, 1 over n. And we denote this limit by L. L equals 0. But this is true specifically for this sequence, and we did it in a very intuitive way. What would be the correct way of showing that a certain value is a limit? For that, we use Cauchy's definition for a limit of a sequence. Cauchy's definition states that for all epsilon that is greater than 0, there exists a natural n naught that for all n's that are greater than n naughts, an minus L in absolute value is smaller than epsilon. From my experience, this definition always scares students. Now, our job here is to explain it and to make it simple. So let's start with the fact that in our present sequence, the limit is 0. L equals 0. So let's work with that. Let's substitute L within the definition with 0. Now we get an minus 0 in absolute value smaller than epsilon, since 0 is our candidate for that limit. So let's draw a line. L equals 0. That value which this sequence's elements tend to. Using some algebra, we eliminate 0 from the definition, and opening the absolute value will result with an greater than minus epsilon and smaller than epsilon. Okay, now we're going to an area that we saw in the previous lesson. An, the elements of the sequence, are bounded by epsilon and minus epsilon. So now we understand the role of epsilon in the definition. Let's draw epsilon and minus epsilon in this sequence. The role of epsilon, or the line epsilon, is the role of the upper bound of the sequence, while minus epsilon is the lower bound of this sequence. Now let's read the definition from the beginning and slowly understand it. The definition states that for all epsilons, there exists an n naught, that for all n's that are greater than n naught, an is bounded by epsilon and minus epsilon. Now we have in front of us an arbitrary epsilon. If we examine the definition, what we need to ask ourselves is, can we find an address, a point, an index, that n naught, that from that point onwards, for any n that is greater than n naught, an would be between epsilon and minus epsilon, basically bounded. Here we don't want the entire sequence to be bounded, only from a specific point. And I notice that for this specific epsilon, yes, I can find that point. I can find that index. If n naught is for A4, which is inside that area between minus epsilon and epsilon, all the rest of the elements in the sequence that follow would be also between minus epsilon and epsilon. Great, that's the idea. However, notice that the first part of the definition states that for all epsilons greater than 0, we need to find that point, which means that if we were to choose a smaller epsilon, the challenge would be a little bit greater. We'll have to walk further to find that starting point from which the rest of the elements are within that area between minus epsilon to epsilon. In this case, it will start only for n naught equals 6. Only from A6 and onwards, the rest of the elements, all of the following elements, will be between minus epsilon and epsilon. Generally speaking, the smaller epsilon is, the more challenging it is to find that point, that from which and onwards the sequence is bounded. And that's the idea behind the definition. So let's continue. Decrease epsilon even more. And now we notice we need to work even harder to find that an that from which the sequence is bounded. And I notice that if n naught is 11, from that point onwards, the sequence is bounded. Now, a very important point to make is that not only the 11th element provides us what we need, also the 12th, the 13th, and even the 20th. Any of them would have been a good choice to make in order to make sure that for that epsilon, we have that n naught. We care less about efficiency here in this topic. More we care about is, does it exist or not? And we'll see in complicated questions that a lot of times we prefer to choose a larger n naught than would expected because it makes the calculations a little bit easier. And we're allowed to do that. It doesn't really matter how far to the right we go, as long as we find one. Now, I think we can agree that in this sequence, doesn't matter how small epsilon gets, we can always find that n naught that corresponds with it. Yes, we don't do it mathematically right now, and we're talking about it intuitively. But if we can do that, even intuitively, that means the limit exists and the sequence has a limit. And that is Cauchy's definition. And if we understand that, we took a big step forward in our mathematical understanding. It might feel that we can use this definition to show that every sequence has a limit. But that's not always the case. In our next lesson, we'll explore a sequence that doesn't have a limit, and we'll understand it using Cauchy's definition. And that will open a door for us to understand what partial limits are. So, see you then.